take a look at the binomial distribution. Now, a binomial distribution results from a procedure that meets all of the following requirements. All right. The requirements are the procedure must have a fixed number of trials, and we're going to call that fixed number of trials n. The trials must be independent, which means that the outcome of any individual trial won't affect the probability in any other trial. Number three, each trial must have all outcomes classified into two categories, either success or failure. Success we're going to denote S, failure we're going to denote F. The probability of a success remains the same in all trials. All right, so let's take a look at this example, number six. And we're going to try to determine whether or not the given procedure results in a binomial distribution. All right. If we don't have a binomial distribution, we're going to identify what requirement is not met. So let's go through the requirements for number six. Clinical trials of Lipitor, treating 863 subjects with Lipitor and asking each subject, how does your head feel? Well, let's see. We have a fixed number of trials, definitely. So one is definitely met. So we can cross one off. One is met because we have 863 uh, trials, fixed number of trials. The trials are independent. Well, I mean, if you're asking them the question, how does your head feel? I think one person's answer um, is not going to affect the probability that a certain other person answers a certain way. So I would say these trials can be reasonably considered, if done scientifically, to be independent. So independence is no problem. Let's see. Each trial must have all outcomes classified into two categories, either success or failure. Well, let me see, how many different outcomes can you have here? Well, you could have anything from great. Well, you could even have things better than great, right? You could have great, you could have okay, and you could also have bad, right? And you could have anything in the middle of these actually. Great, okay, bad, and anything in between. So there are many different outcomes here. So this one is not met. So number six is actually not a binomial distribution. Maybe some other kind of distribution, but it's definitely not binomial because it doesn't meet the requirements. All right, now let's look at number eight. Number eight, treating 152 couples with Y-sort gender selection method developed by Genetics and IVF Institute and recording the gender of each of the 152 babies that are born. Okay, well, let's see. We have a fixed number of trials here. We have 152 births. So that's N. So this checks out. We have a fixed number of trials. And let's see. We're recording the gender of each child. Well, the gender of each child, I believe, is independent of the gender of any of the previous children. The probability of having a boy or girl is going to be the same regardless of if you've had a boy or girl before or not. So independence checks out. Each trial must have all outcomes classifiable into two categories. So we can only have two outcomes possible. And in this case, the two outcomes would be either male or female. Male or female. So this one checks out. And the probability of a success remains the same. So the probability of getting a male or a female will remain the same from birth to birth. So this one checks out also. So this one turns out to be binomial. So just because it meets those criteria, we can say that this is a binomial distribution. Number eight is binomial. All right, let's see. The last one. The last one, we have surveying governors. Let's see whether this one can be treated as binomial or not. Well, let's see. Surveying 15 different governors are randomly selected from the 50 governors currently in office, and the sex of each governor is recorded. Well, once again, we're dealing with sex. 15 different governors are randomly selected from the 50 governors. We have 15 out of the 50 randomly selected, and we have a fixed number of trials. 15 different governors are randomly selected from the 50. So we do have a fixed number of trials. 15 is the fixed number of trials. We're going to have 15 governors that we're going to look at. Okay, let me see here. We also have, oh, actually, let's see. This one checks out. The independence part. The trials must be independent. Hmm. The outcome of any trial does not affect the probability in any other trial. Well, if we only choose 15, if n is 15, then depending on how many female governors there are, male versus female, let's say for instance there are, I don't know, 7 male governors and 8 female governors for a total of 15 governors. Well, once we've chosen the first governor, our total of 15 governors um, goes down to only 14 governors now, because we can't select another governor if we replace that first governor and allow that governor to be chosen again. That would make any sense, because we wouldn't have 15 if we did this with replacement. So 14, and then if we chose a female governor, then there would only be 7 female governors left. So the new probability would be on the second trial. The first trial would be 8 out of 15. Oops, 8 out of 15, because there would be 8 female governors out of a total of 15 governors. But on the second trial, there would be 7 14th, 7 out of 14. And we would see that the probability of getting a female governor would change from trial to trial, so we would not meet this criteria. And also the probability would not be independent, so we wouldn't meet this criteria either, because what happened on the first trial affects the probability on the second trial. So even though we have the case here where we have male and female as the only 2 possible outcomes, male and female are the only 2 possible outcomes here, also just like in number 8, but in this case the trials are not independent. So this one, number 10, is not binomial for that reason. Okay, now sometimes you can treat things that are not binomial as if they are binomial by going by this 5% guideline. All right, treating dependent events as being independent, the 5% guideline for cumbersome calculations. Now, if the calculations are cumbersome, and if a sample size is no more than 5% of the size of the entire population, treat the selection as being independent, even if the selections are made without replacement. So what we're going to do is we're going to look at number 12 here. We have a survey of 200 statistics students. So this is the sample size, 200 statistics students. So we have 200 statistics students, and we're randomly going to select them and ask them if they own a TI-84 plus calculator. Now, if we ask them that particular question, there are only 2 outcomes. Either they answer that they do own one, yes, or they do not own one, no. Or you could look at this as being a success or a failure. If they do own one, you could call it being a successful trial. Success equals yes. Or you could call, a failure an answer of no. These trials are, in fact, not independent. So we cannot, in fact, use the binomial distribution unless we apply the 5% guideline, which says that we can treat them as independent as long as the sample size, which is n, is no more than 5% of the size of the entire population. And this population would be the population of all statistics students. So indeed, the 5% guideline can be applied. We could treat this as binomial, even though it is not strictly a binomial distribution. All right, so that is the 5% guideline. All right, here's some notation we're going to use for the binomial distribution. Um, S and F are success and failure. They denote the two possible categories of all outcomes. The probability of a success, well, the probability of a success, we're going to just denote lowercase p. So in the binomial distribution formulas, when you see lowercase p, they're talking about the probability of a success. Um, the probability of a failure, which is the complement of the probability of a success, so it's 1 minus the probability of a success, which is p, we're going to denote q. So we have p and q. P is the probability of a success, q is the probability of a failure. N is going to denote the fixed number of trials. X denotes the number of successes that you want to have in n trials. So x can be any whole number from 0 all the way up to n, including 0 and n. P denotes the probability of a success in a single trial. Q denotes the probability of a success in a single trial. And px denotes the probability of getting exactly one success among n trials. So we have two probabilities going on here about success. Lowercase p is the probability of a success in each of the individual trials. So lowercase p is the probability of a success on a single trial. And q is 1 minus p, like it says up there, 1 minus p. But px, the function, is actually the probability of getting x successes among n trials. So px, the probability function here, and lowercase p denote two different things. Lowercase p is going to be a fixed number, but px is going to be the functional value. It's a probability function. All right, so let's see. Here's one way of calculating binomial probability. This is table A1. It's in the appendix of your book. And assume that the procedure yields a binomial distribution with the trials repeated n times. In this case, n is going to be 14. Use table A1 to find the probability of x successes, given that the probability p of a success on a given trial is on the table here. So this is the probability p of success. We want to see what the probability of getting x successes in n trials. So what we're doing is we're running a procedure 14 times, and we're going to see how many times, we're going to see if we, what's the probability that this procedure results in a success exactly 4 of those 14 times if the probability of a success is 60%. Well, looking at the table, the first thing you want to do is you want to find n. N is in the first column of the table. See, n is in the first column of the table here. And what we're going to do is we're going to look down and we're going to look for our n, which is 14. So n is 14 is right here. So we know we're going to be working in this block of the table here. These are the x values in the next column. So x is 0 is here, x is 1. We want x is equal to 4. So we're looking at this row right here. We're looking at the row where x is equal to 4. And we're looking at this row right here. I'm making a line under the row that we're looking at. All right? So x is equal to 4 is the row above that black line. That row is x is equal to 4. So I have n found, which is 14. I have x found, which is 4 under the 14. And now I'm going to find my probability, which is 60.6. That's the probability of a success on a single trial. So I'm looking up at the top here. You see up here, we have going across the top in the top row, p. So these are values of p. So I just need to find 0.6 for my 0.60 for my value of p. So let's see. To the left of this line, we have those are, that column there represents all the probabilities of x, where the probability of a success in one trial is equal to 60%. So let's see, we're looking at this row and this column. This value right here is the probability we're looking for. So the probability of getting 4 successes in this binomial experiment is 0.014. So if there are 14 trials, the probability of getting 4 successes is 0.014. All right, now here's the binomial formula. This table comes from this formula. If you use this formula to do all these calculations for these n's and these x's and these p's, then you would get this, or sorry, if you use those calculations, you would get this table if you use this formula with n, x, and p. So what we're going to do now is we're going to actually use the formula to actually come up with the probability that we were just getting from the table. So this is formula 5.5 in your book, and it is the probability function that I was talking about. So notice this is the function p of x, but this p over here denotes the probability of a success on a single trial. All right, x denotes the number of successes that we want to have in our n trials. N is the fixed number of trials. All right, so we have all these things, and now let's go ahead and use the formula to calculate a probability. All right, let's see the probability of x. So we're looking for the probability of 2, because x is equal to 2 in this case. And this says it's equal to n factorial. Well, this thing here is actually the combination. This looks like n cx. So if you can find the combination, you can do that. I'm going to write it as that, as ncx. Most of your calculators will do that. ncx. And then we'll have p to the x. Well, p is 0.35, 0.35 to the x, and x we said was 4, or 2, sorry, 2. So actually, we can replace this down here. This x we can replace with 2, and this n is actually given to us as 9. So we're actually looking here at 9, choose 2, and then 0.35 squared, and then q is 1 minus p, so that's 1 minus 0.35 to the n minus x. N is 9, minus x is 2, and this is equal to, well, let's see here. We have first 9 choose 2. 9 choose 2 is 9 times 8 times 7 factorial. And in the denominator, I have 9 minus 2 factorial, 7 factorial, times 2 factorial. So let's see. This is going to be multiplied by 0.35 squared. 0.35 squared is, let's see, 0.35 squared .1225. And then we have 1 minus 0.35. 1 minus 0.35 is 0.65. So we have 0.65 here. And 0.65 to the 9 minus 2 is to the 7th power. All right, let's see what we have here. All right, so this is equal to 9 times 8 times 7 factorial divided by 7 factorial times 2 factorial times 0.1225, and then 0.65 raised to the power of 7 is 0.049. 0.049. All right, let me see here. This 7 factorial cancels the 7 factorial. And we get 9 times 2 goes into 2 factorial is 2, and 2 goes into 8 4 times. So this numerator here is just 9 times 4, which is 36. And let's see, 36 times 0.1225 times 0.045. Let's see what that yields. 36 times 0.1225 times 0.045 is equal to 0.1984. So let's see. So let's round that to 0.198. 0.198. Let's get rid of you. 0.198. So this is equal to 0.198. Alright, so that's how you use the formula to calculate probability. And now we're going to use a little bit of technology. The formula, I don't like using the formula myself. It takes a while and it can be quite cumbersome. So let's take a look at how to use the TI 84 plus or the TI 83 also. These directions will also work for. So this is how to use the TI in order to come up with the answer. All right, to a binomial problem. So here's number 29, and here are the directions for doing it on the binomial. You can pause this video, you can do whatever. But let's take a look at this on the TI calculator here. Let's take a look at that. And let's go ahead and go to this mode here. All right. Okay, so let's move this over, and let's move this question over. And here we have our TI. All right, so let's go ahead and follow these directions here. So, um, brand recognition. The brand name of Mrs. Fields Cookies has 90% recognition rate based on data from the franchise advantage. If Mrs. Fields herself wants to verify that by beginning with a small sample of 10 randomly selected consumers, find the probability that exactly 9 of the 10 consumers recognizes her brand name. Also, find the probability that the number who recognize her brand name is not 9. All right, let's take a look at this. We have a fixed number of trials. We will have a sample of 10. So there we have n. N is the fixed number of trials. They say 90%. 90% is P, the probability of success, the probability that somebody recognizes Mrs. Fields' brand. And they want to know what the probability that exactly 9. So this is going to be X. So I have everything I need. I have X, N, and P. Now I'm going to put all of this into my calculator. So let's turn on our TI here. Let's turn this on. All right, and then it says to press second. So we're going to press second, which is this yellow button here on my calculator. So here is second right here. And then from second, we're going to hit distributions, which is above vars. So we're looking above this key right here under the arrows, the key that says vars, to see where it says distributions. All right. So let's use an eraser and get rid of that. So we're looking at those two keys right there, all right? So let's get back to our pointer. So we hit second, and then the arrow comes into the cursor here. And we're going to hit the button that says vars, and above vars it says DISTR. And we're going to look for binom PDF. So we're going to scroll down with the arrow until we see binom PDF. Here's binom PDF right here. We press enter. So binom PDF, and it says we need to put in N, P, and X. Well, those are the three numbers that I just found. N is 10, P is uh, 90.9, so let's put point 0.9. And comma, notice I'm putting commas between them, N comma P comma X, and the comma is right here. The comma is above the number 7. And then X is 9, so let's put in the 9 here, 9. And then we close the parenthesis, and we press enter. And it gives us the value 0.378. So the probability that exactly 9 of the customers recognize the brand Mrs. Fields is going to be 38.7%. That's the probability. So, okay. Now let's take a look at some of the other functions that it says the calculator has. It says we can also do binom CDF, and that's the cumulative distribution. So if you want the cumulative probabilities, which are the probabilities of that value and all the values below it summed up, use the binom CDF.